Alright, so over the past 2 days, what we have done is look at the roots and zeros of a function. The other day we discussed that the degree determines the number of roots and zeros. When the graph crosses the x-axis, those are called the real roots. And then when it does not, but there's still a root, we call those the complex. Those occur above or below the x-axis. Those involve our i's. The number of real and complex roots must sum to the highest power degree. Complex roots must always come in pairs. So if you're only given a single root or you only find a single root, then you need to find its matching conjugate pair. So we discussed complex conjugates. Yesterday, I had you watch a short video discussing how to take the roots of a polynomial and work backwards. So we took the roots of the polynomial and we worked backwards to find the original function. And then what we're going to do today is something called Descartes' rule. And essentially what it is it's a way of determining the number of real and imaginary solutions by looking at the signs of the function and their alternating patterns. So for Descartes' rule, what we're going to do is arrange the terms of the polynomials from descending degree. So you're going to arrange the terms of the polynomial in descending degree. The number of times the coefficient of the positive term changes signs determines the number of positive real roots. The number of times the coefficient of the terms p of negative x changes signs is the number of negative real roots. So this doesn't help us with the complex. It determines the number of positive and negative real roots. When I mean a sign change, I mean if it goes like x cubed minus x squared, then that's a sign change because x cubed is positive and x squared is negative. But then if it would say minus x, that's not a sign change because it goes negative x squared, negative x. So let's talk about this example here. So if we look at x to the 6th to positive 3x to the 5th, that is not a sign change because it goes positive, positive. Then on the next one, it goes positive x to the 5th, negative x to the 4th. So that is considered the first change. From a negative x to the 4th to a negative x cubed, it stays negative, negative, no sign change. Then here, negative to a positive is a sign change. Positive to a negative is a sign change, etc. So, 1, 2, 3, 4 sign changes means that this graph could potentially have 4, 2, or 0 positive real roots. It cannot have 6. It can have 4, 2, or 0. What we're going to do now is plug negative x into this equation. So we can look for the negative sign changes. So if you plug negative x in, every time you have a negative, so what you're going to do is put a negative x in for all your x's. So go ahead and write that down. Any positive powered number, whether it is a negative plugged in or a positive plugged in, will always be positive. A negative variable to an odd power will maintain its negative, so then the power or sign of the coefficient will matter. Like in this case here, the negative x cubed will stay negative, but a negative 6 times a negative x cubed will become positive. So cleaning that up, negative x to the 6th is positive x to the 6th. Negative x to the 5th stays negative times a positive, so it's negative 3x to the 5th. Negative x to the 4th just becomes positive, so the negative 4x stays. Negative times a negative became a positive 6x cubed. Anything even squared is positive. A negative times a negative is positive. And then the 5 doesn't have a variable, so it stays positive. And now what we're going to do is go back and look for sign changes on the negative aspect. So we have one sign change here, none. Another sign change here, none, none, none. So in all, there are 2 sign changes, which means I could have 2 or 0. And now this time, we're talking about the negative real zeros. So what that does is give a variety of combinations of solutions to this problem. So we're going to compare the number of real, positive, real negative, and complex. So you could have the number of real, the number of negative, the number of imaginary, and the total. So in the case of this problem, we can have 4, 2, or 0 in the real column, 2 or 0 in the negative column, and the imaginary must always come in pairs. And the total number cannot exceed 6. So, the max number of real zeros would occur if you have all 4 positive and all 2 negative. So if I have 4 positive and 2 negative, that leave 0 imaginary and 6 real zeros. The alternative is to keep 4 positive zeros, but have no negative zeros, which means we'd have 2 imaginary. So that graph could look something like that, or it might up here have like a little blip going on. The next option would be to only have 2 real positives, 2 negatives, sorry for that one. It needs to be that way, sorry. Because I said 4 positives. This one would look like that drawing. So you have 2 positive, 2 negative, and 2 imaginary. In the next case, same idea. 2 positive and 4 imaginary. So that means it only crosses on the positive side. It still ends above. So you might have like some bumps going on up here. And then you can have the case of none and none. So that's where your graph is entirely above. If there's no real and no imaginary and all complex. And then this one would be like the flipping of that one. Okay? So a lot of times we're going to try to determine the number of negative and positive reals so we can determine the number of imaginary. Not all of them are going to be as complex as this, but you can see that we have, 6 total different combinations of real and imaginary zeros. Okay, so let's look at that next example. So if you look just at f of x to start, then we could determine that there is a sign change from here to here. But what's happening is we are missing x squared. So you have one of 2 choices. You can either factor this out, or you have to imagine a missing number. So that you can see we have a sign change from here to there. Or you would see that original. So we know that this is going to have 1 real positive. We can plug in f of negative x. when we plug in f of negative x, we get negative x cubed plus 4x. So that determines another sign change. So that tells me that I have one negative real. And then the tricky one are zeros. Zeros don't count as positive or negatives. So what hopefully you see here is that we can take out a GCF of x. The sign changes still don't change. It's just that when we factor that, it will not account for my negative. Therefore, when we factor this, we have our positive root, our negative root, and our 0. So when you have a GCF of x, you just have to count that as a 0. Okay? If a polynomial is not factorable, then we use the technique we talked about in 6.6. That technique is to synthetically divide. So if we know one of the roots, then we can use that root to synthetic. Now we can also look at this problem and determine the number of roots. So if you compare x cubed to negative x squared, that gives you 1. This goes negative to negative, so none. But once again, negative to positive, so 2. So 2 sign changes tell me that this has 2 or 0 positive reals. If I look at f of negative x, I have 1 sign change. So that tells me I have 1 negative real. So I'm going to have 3 real, or I'm going to have 1 real and 2 complex. But since the one root I'm given is positive, then that tells me that I can have 0 positive because they have to have 2. So whenever you get your numbers, they have to decrease by 2 or increase by 2. So if this was 3 negatives, then the options would be 3 or 1. That was 2 or 0, but because I was given 1 positive, I know I have to have 2. So let's do synthetic. 5 goes in my box. This was x cubed. So that tells me my power is now x squared. So I get x squared minus 2. So then this goes over and you get x squared equals 2. So this is solving by taking the square root. Then we get x equals plus or minus the square root of 2, which does in fact give me 2 solutions. One at positive square root 2 and one at negative. Okay?
I use the restroom?
Yeah. So that leads us into the complex conjugate theorem. Again, I'm just reiterating that yesterday and 2 days ago we talked about the fact that complex conjugates have to come in pairs. Complex conjugates have to come in pairs. So if you are going to have one imaginary solution, you have to have its pair, that is its conjugate. So the conjugate is A plus bi and A minus bi. Notice that the sign of A does not change. The only sign change is on the imaginary part. So let's look at a pair of complex conjugates. And let's talk about, sorry, I can't minimize, how they work. So if the known root is imaginary, then we can use the complex conjugate theorem. So if one root is 4 minus I, then we also know that the other root is 4 plus I. My I somehow got tagged on over here. So we have 4 minus I and 4 plus I. So down at the bottom it said find all roots. Well, if one is 4 minus I, then another one is 4 plus I. So if this has a power of 3, we already know 2 of its roots. Now what we need to do is determine if the final root is positive or negative. So what we're going to do is look at the sign changes. So I have a sign change here and a sign change there. So that tells me if I have positive real roots, I have to have 2 or 0. Well, since I already have 2 imaginary, I can't have 2 or 0 positive. So what we're going to do is look at negative x. If I plug in negative x into x cubed, it's negative. A negative into x squared doesn't change it. A negative times a negative for the 7 makes it positive. And then the 51 stays as well. So no change, change, no change. So that means that I could have 1 negative real. So that tells me that this function has 2 imaginary and 1 real negative. And I want to find what that real negative is. So what we could do is kind of the idea of what we did yesterday. We can take our 2 complex conjugates and we can multiply them together so that we can get a quadratic. So what we could do is take our 2 complex conjugates and multiply them together like we did yesterday to get our quadratic. So go ahead, take a minute and multiply those. I'm going to bring that up for you. Together. Take a minute, multiply those together. And then one of our techniques was that we could use long division and synthetic division to find another factor. Well, since we have a cubic and our factor is a quadratic, we can't use synthetic. So what we're going to do is use long division to find the missing negative factor. So what you do is put the function inside. The divisor, or what we know is a factor, outside. I know the remainder is going to be 0 because I know that this is a factor, because I was given that 4 plus or minus I were roots. So it goes back to what we said before. What do you multiply x squared by to get x cubed? You multiply by x. Then you distribute the x in. So you had x cubed minus 5x squared minus 7x plus 51. So the third root is negative x, which matches our theorem that we need a negative value. Okay? For your homework, most of what I want you to do is just tell me the number of real and imaginary. And then for a couple of them, you're finding the zeros. Okay, so you have time to do that now. I'll be back here if you get stuck. The 33 to like 42 is more like what we did now. And then that back page is what we did yesterday, where it's giving you the roots and you multiply backwards. So I did 34 for you to kind of give you another example just to talk about. So like 34, what I did was compared the positive and the negatives. So I got 2 or 0 positive reals and 1 negative real. This is what we're going to talk about tomorrow. So with the positives and negatives, oftentimes our factors are going to be 1s or -1. So I went with guessing x minus 1 or a positive 1 was a real, and I got that it was. So then I used that to get to factored form and find my other solutions. For 33 to 42, you can use your graphing calculator to get you 1 positive or negative real, so you can do synthetic. So like to get you started, since the textbook doesn't give you one, you could use a graphing calculator to get one.